Hello everyone and welcome to We Meet at Digital Days. My name is Lisa Richter and I will moderate this presentation. We are very pleased that you took the time to participate in our virtual conference. The topic of this presentation is Better Safe Than Sorry, Practical EMC Design Considerations. Our speaker is Mohamed Al-Alami. He will hold a presentation and will answer your questions. Before we start, I would like to point out one thing. You will be muted during the presentation. This means that you cannot ask questions via microphone during the presentations. Nevertheless, you have the opportunity to ask questions during the presentation at any time via the chat function. You will find the chat function in the control panel. This presentation will be about 30 minutes long. The chat questions will be answered in a Q&A session following the webinar. There are 5 to 10 minutes in addition scheduled for this. If we are unable to answer all of your questions within this time, we will answer them via email afterwards. If you still have any other questions left, just mail us at exhibition@we-online.com. We will try to answer all of your questions promptly. At the end of the presentation, you'll be asked to participate in a feedback survey. We would be pleased if you take the time to fill out a survey and help us to improve our event. You will receive the presentation in the next few days, and the recording will be available at our website shortly. So now we'll hand over to our speaker, Mo, and I wish you an exciting presentation.
Good morning, everyone. Thank you for joining my presentation. Let's just start from the very beginning. Oops. And hope everybody can see the presentation.
Yes, we can see it.
Excellent. So the agenda for today, what are we going to talk about? We're going to start off by looking at the practical aspects of EMI filter design. We'll look at the architecture, but the architectures of filters are fairly basic. So what we are looking really at is what is different from a practical point of view that we need to take into consideration. And that theme is going to cut through the remaining sections, be it selection or simulation. I'm not looking to simulate a simple LC filter that's basic, but we're looking at what is different about what we need to do to get a better result out of that simulation, out of the selection. Then we go into a very key section of today's presentation, layout and tracking, something that a lot of people unfortunately maybe leave to the very last bit and the very end of the design naturally, or they don't consider, I should say, very much when they're doing the layout and the build of the PCB. Very critical. And we'll do this via a practical example using a PoE type 2 flyback converter that I've designed for one of our customers. We look at the design for the filtering for that power stage, as well as the power stage itself, and the signal integrity. We'll finish off with just a run through very quickly the general interfaces, things like USB, Ethernet, CAN, etc., and what solutions Würth can offer you from an EMI point of view for those interfaces. So without any further ado, let's start. Okay. Practical EMI filter design. Now, better safe than sorry is what I started the title for this presentation with. Why is it better safe than sorry? It's my own experience with EMI side of things. I've always found that, and I'm seeing working with customers or as a designer or power supply designer in the past, if we leave EMC to a very late stage of the design, then we end up suffering for it quite substantially, particularly from a cost point of view, with potentially PCB redesign, sometimes even metalwork changes. While if we consider this at an early stage, we're in a much better position. So I am not an EMC necessarily design or test engineer. I come from power supply design and development. EMC came in, I guess, for my sins. But with power supply design, we always look at EMC filter design. That's what we're going to be talking about today, and considering hopefully in a very early stage of your design process. So architecture-wise, what should we design? What should we consider practically when we're designing? We should consider multiple stages. What do we mean by multiple stages? Stages that would consider both conducted as well as radiated emissions side of things. Those stages will also need to account for common mode as well as differential mode. We can't just look at, just throw in a common mode choke there. We also need to think about over voltage protection. A lot of people leave this. I see so many filtering, good filtering on boards without any transient voltage suppressors or ESD suppressors. And of course, we need to consider layout and tracking, as we will see later on today. That can make or break a design or even a good filter's performance. It can compromise a good filter's performance. And finally, we also need to consider the practical component and functional shortfall. What do I mean by that? Components have got parasitics. We need to consider those parasitics. That's a major theme of today's presentation. So we're looking at those and considering those as part of putting together our filter, and also as well the impact that that filter can have on the intended functional performance of my design. I don't want to damage my Ethernet data transmission because I want to put a filter there to get rid of EMI. I want the cake and I want to eat it. I want to filter out the EMI and I want to get a good performance from a data transmission point of view. That's what this means. And we will look at these as well, time permitting. Quickly on something that's very simple, signal propagation. What types of noise do we have out there? What modes of transmissions do we have? We all know common mode, we all know differential mode noise. These are the types that we need to attenuate. So just as an example, just to show you here on a USB transmission line, the common mode noise is noise transmitted on both data plus, data minus, plus or minus lines, for example, coming back through ground, chassis, etc. While the differential mode noise is the noise associated with the return path of the actual signal. So it's differential signal noise on the plus and returning on the minus. Both of these types of noise we will need to find filtering for, or put filtering together for. Okay, starting off with the differential type filter topologies. Again, this is very basic. I'm just putting together a representation of these for you, an LC or a ferrite with a capacitor, pretty much the same thing, or a pi or a T or a chip bead ferrite by itself or a little MLCC by itself. All of these are differential type filters that can be used to attenuate differential mode noise. Common mode side of things, you need a common mode choke. That's the cornerstone of your common mode insertion loss or attenuation. A common mode choke works slightly differently from a differential way or the differential attenuator. In common mode, the choke is designed such that when you've got differential noise, as you can see here in red, going through the choke does not attenuate that. The flux within the core cancels out. Well, almost cancels out. We will find out later that nothing is perfect. We always have parasitics, as I promised you at the beginning. But however, when I put in my common mode noise flowing in the same direction through my common mode choke, that's when the common mode choke wakes up and starts doing all sorts of things, attenuates that noise and converts it into heat or attenuates it using the LC behavior, as we will see in a little bit as well. Okay. Selection, next section on architecture. After architecture is selection. So component selection considerations. What should we consider when we are selecting the components? I'm not talking about the amount of impedance that we need, at what frequency, this is basic, or what inductance do I need, what capacitance value do I want. Okay, that's a very basic effects. I'm talking about the practical things that sit behind the component. Things like DC bias effect on a chip bead ferrite, for example. Or a parasitic effect, the leakage inductance of that common mode choke we've just seen on the earlier slide. Temperature, impedance versus frequency, the whole of that characteristic. How is that looking? And most importantly nowadays, now if I put this as a poll to you guys over this platform, what would you say as the most important aspect of component selection in today's market? I think everybody would agree it's availability and stock. So all the customers and engineers I come across are embroiled in this, and we know it's a big issue at this point in time. Hopefully we'll be able to help you with this, but this is not for today's talk naturally. But this is a challenge as we are seeing in today's market. So let's start off by looking at the DC bias effect. These are the impedance characteristic curves for one of our chip bead ferrites. That's the part number that you see there. And what we're trying to show you here is the impact of putting DC current through these ferrites. That changes the whole impedance characteristic. It shifts the impedance quite substantially down, as you can see here. We just use the laser pointer. So we're going substantially down in impedance, and it shifts the self-resonant frequency up. So you're getting a totally different characteristic to what you would expect to see, unless you are able to identify this impact of DC bias current. Very, very critical when you are putting together your high frequency filter, or you're designing this as part of a high frequency radiated emissions filter. In temperature. Also staying on the same type of component, a chip bead ferrite, but this is also applicable to cable ferrites or any split ferrites or solid ferrites. The concept is the same. With temperature, what we see here is as you increase the temperature, the impedance drops down quite substantially. So this is minus 55 degrees. I'll zoom in a bit so that you can see better. There's a minus 55 degrees here and going up to 160 degrees Celsius. So there's a quite substantial drop in the impedance behavior of that ferrite, be it a chip bead ferrite or a cable ferrite. Now, the odd thing is that behavior flips on its head during the inductive reactance zone of the behavior, the XL behavior in the lower frequencies. That's not for today. We can talk about this hopefully in a future seminar, but this is really where the business end is of our chip bead ferrite. So that's what we're concerned about today. And that's where the bigger impact is as well of temperature. Let's leave chip bead ferrites and go on to MLCCs. That's the other part of your chip bead ferrite C filter, differential filter that we talked about. So with this, MLCCs exhibit a DC bias voltage effect. So the voltage across the MLCC will drop its capacitance by quite a substantial percentage depending on the class of MLCC that you're using. MP0 is very stable, as we can see here, even with temperature, but X7R, X5R, Y5V, we get quite a drop in capacitance. This will impact quite substantially on the behavior and performance of your ferrite C filter. That's a simple filter, but if we don't take into account the drop in this capacitance, then we're shooting ourselves in the foot in that, assuming that we are going to get a certain type of performance when we're not. So that's also another key aspect to consider. Where can you do all of this? Where can you consider the chip bead ferrites, DC bias and capacitors, bias, and all sorts of other things? REDEXPERT. REDEXPERT is a fantastic tool that we have on our website that allows you not only to select components generally using the set parameters, current, voltage, inductance, etc., capacitance value, but it also furnishes you and provides you with a lot more facility to look out for these extra, what we call practical design considerations. The DC bias effect on a chip bead ferrite, how is that going to change its impedance? You'll have the impedance curve right there in front of you. Temperature effect, voltage bias effect on an MLCC. These make life a lot easier for you to consider when you're putting together your filter, as we will see in the simulation section next. So you've got a better understanding of this. Is not going to be 22 microfarads, no way. When I put 10 volts across I put 5 volts across a 6.3 volt MLCC, I'm not going to get that. I'll be lucky to get maybe 10 microfarads, depending on the chip size. So this information is available at your disposal with REDEXPERT. Another beautiful thing about REDEXPERT is, like I said, it's not only that you can see the selection table, the components, and you can compare these components based on their curves and characteristic behavior, but you also have what we call the design tool on the side. Now, what the design tool does for you is it gives you that extra dimension of calculations based on the product range that you are using. For chip bead ferrites, we can calculate what sort of attenuation in dBs that chip bead ferrite is going to give you. The same thing applies for capacitors. The same thing applies for inductors. So you have got this ability to utilize some of these extra functions to help you zoom in onto the most practically suitable component for your design. I've included a link to REDEXPERT on this final slide for you. Please do go in. You don't need to download the tool. It's online, so there's no issue with using it from your workstation at work. All we ask you to do is sign up for the tool to allow you to have all of the great facilities and functionality that I have shown you earlier. That will give you sort of a whole new world of selecting components based on detailed characteristics, which you can down select based on all of the facilities within REDEXPERT. One final thing to mention about REDEXPERT is we have recently introduced an EMI filter design tool within REDEXPERT. It's really good because you can select various different filter topologies, an LC, a pi, or a T, a two-stage, a four-stage filter, second order, fourth order, and so on. And based on your spec requirements, you can enter a certain amount of attenuation, for example, at a specific frequency, your input voltage, current, etc. And the tool will return an inductor and a capacitor that would be suitable based on your spec requirements or your design requirements. And it will produce a report like you can see here, or a summary that you can save as a PDF and attach it to your final report when you're putting together your functional report for your design. Simulations, moving on, next section. So we said we are going to simulate all of this behavior once we have selected these components to look at conducted, radiated emissions. Another very key aspect to look at is damping, as you will see over the next few slides. We'll need to look at the leakage effect, which I also mentioned. That's the leakage effect of the common mode choke. Oscillations and instability, that's the functional shortfall. And we'll also just very quickly run through the time domain behavior. We always look at things when it comes to filters in the frequency domain. Let's look at this in the time domain, just to give you a different flavor. So the first practical point to look out for when it comes to common mode filter design is if it is the case that you do have a common mode filter design with a separate chassis ground available for your unit. And in that case, you are using common mode capacitors down to that chassis ground. So you have got that facility in this case. So you're taking full advantage of attenuating common mode noise, not just with a common mode choke, but with the caps as well. This is where it's also important, and it's practice that we have used in the past, is to have these filters damped with an R and a C. Now, the idea behind the damping, and you can do this very quickly and simply, as you can see here in LT Spice, is run the simulation. You will see without the damping, you get the big overshoot, the resonance at the cutoff frequency. You damp it and you get no resonance. And why is this important? This filter here is meant, based on the selected component, the value of the capacitors, evidently that it is more of the upper conducted and interradiated. This is its business end. So here, it's not doing anything, fine. But what I don't want it to do is make things worse for me, especially at the switching end of a power supply interface, just to take as an example. So this is something important to take into account. That's why we say take care of this. I mentioned the leakage effect. Now, if you go on REDEXPERT, you will see the beautiful curves for common mode impedance, for differential mode impedance of the common mode choke. That's the leakage inductance basically between the two windings. Now that's important as well to simulate, because that leakage inductance which sits here will interact with any differential capacitance that you have here to give me a filter with a cutoff again. And if I don't damp that filter appropriately, again, I potentially end up with an issue in those frequencies. Again, this filter is the same as the previous filter. It's meant to attenuate noise in the radiated emissions and do nothing in the conducted as per the selected types of components. Okay, let's take an example now of a differential mode filter and go through that example. We've talked about things to consider for common mode. Let's turn our attention to differential mode. So this is a very simple example with a ferrite and a capacitor that has been attached to the output of a power supply. Now, I do apologize, this shouldn't say 30, it should say really 5 volts. That's the output 5 volt of a buck regulator, which is supplied from a 30 volt, but I don't care really about the DC here. I'm simulating AC. So I'm looking just as the performance, as the insertion loss performance of this LC, or ferrite C, chip beat ferrite, not really L. And we have also introduced a damping branch here as well for that filter, as we have been talking about, but this is now differential mode. Now we can see the difference between the damped filter in red and the undamped filter in blue. Note the frequency here is 1, 2, 3 megahertz is where this notch is of this filter. Just keep this in the back of the mind. Okay. There is that filter there. That's the same chip beat ferrite. That's the same capacitor, and that's the same damping that we use for that capacitor. We've inserted this into that buck design. I said we've got 30 volts in, 5 volts out. This works from 50 milliamps to 5 amps is the maximum. But we ran this simulation in the time domain just to show you a difference and the impact that that notch that you saw on that filter response is going to have in the time domain, which is really what's key for us, the noise that we're seeing on that output voltage. Okay, here is the timeline for the output voltage on that buck regulator. Now we can see there's a lot of noise on this output voltage. This is intentional. We have made it noisy because we want to see the impact of the introduction of the filtering on the output. So as you can see, as we introduce the chip beat ferrite by itself on the output, noise drops down. When I introduce the output 10 nanofarad capacitor, the noise disappears and I've got a nice clean 5 volt output. Lovely. Where is the problem? I start introducing a dynamic load transient, a switching load at 3 megahertz. Now I'm seeing all of that noise come through. Now I damp because I wasn't introducing the damping here. Here I've introduced the 3 ohm damping resistor and 100 nan damping capacitor, and the noises come. So this is just showing you the importance of this. To finish this section off, I'm just showing you the overall recommended, I guess, architecture for a radiated emission type filtering. This is the same. The only difference here is if you have got the facility to have a chassis and introduce the extra branch of common mode capacitors. You select the suitable common mode stage with the chip beat ferrites differentially, as well as the capacitors damped differentially. So that's the radiated emissions side of things. We shift to the conducted emissions side of things, and this is where functional performance becomes also critical. Now, damping we talked about before is important, but here it is critical in the sense that with the conducted emissions proper L and a higher value of C, now we are creating a filter that can cause an instability in our power stage. This is going to be an input filter. That input filter needs to be damped, as you can see with the extra damping branch here. That is an undamped, and this is a damped filter. And the reason for this damping, you will see on the next slide, is that a power supply, DC-DC, buck, boost, whatever you might have here, presents itself as a negative load impedance to the filter, which is placed on the input here. So that being the case, what that does is it can cause these oscillations if that filter is not suitably damped. Now, it is not always the case that you require this damping. It's a function of multiple different conditions or operating conditions, but it's always better to be safe than sorry. I would say introduce this extra component, the capacitor and the damping resistor, and if you don't need them, not fit them, easy. Now I'll show you this in the time domain. Again, the same design as we had before, but now we have got the LC filter on the input side here. There is the L, there is the C, and I've got a 27 microfarad aluminium electrolytic. That aluminium electrolytic is going to give me my damping through its own ESR. That's a possibility sometimes, but you can also use a separate low ESR capacitor and an external resistor. That's my preference because I've got better control then. With the ESR of an aluminium electrolytic, we know it can change quite substantially, particularly with things like temperature. And this is what you get in the time domain again. I'm promising you to show you what happens in the time domain. In blue, the filter is damped. In red, the filter is not damped. And what you see is the output here is nice and stable. The output here is oscillating. It is not stable at all, as I promised you from the earlier slides. I'll finish off this section with just showing you also an example of an LT-SPICE simulation of a mains filter that I have done also before. So this is not just always applicable to a standard DC interface. You can also implement it on a higher voltage type interface as well, mains. Now, second section, layout and tracking, and I can see that I'm well behind time. So what I'm going to do in layout and tracking is just give you or present you the example of that Type 2 PoE flyback converter that I designed for the customer based on the LT3758A chipset. It's a constant switching frequency. The specs, design requirements were 9 to 30 volts in, 12 volts out, 1.5 amps, but we tested up to 2.5 for expansion for future. And the maximum efficiency was required 90%. We achieved around 87. This is the power stage that I had designed. You can see it here. And you can see also that I have included the leading edge spike clamp, the snubbers for both that spike and for the diode spike. We've also got a filter as well, an RC filter for the current sense signal, beg your pardon. So good design practice has been followed, in other words, from a power stage point of view. On the next slide, you will see the filter design. This is the EMI filter that sits on the front end of that power stage. And in here, you can see the over voltage protection has been included, common mode, differential mode stage, capacitors, as well as the damping for both the differential side, as well as the common mode capacitors down to chassis. We had a chassis for this particular design. Okay. So the next step was to simulate this design using LT-SPICE. So this is the power circuit being simulated. This is just an indication of where that EMI filter would sit. But to give you a warmer feeling, I'm a firm believer with simulation, garbage in, garbage out. Unless you use reasonable models for parts, then you're not going to really get a representative output of the simulation. Having said that, this is what happened with the transformer model. It has been modeled with leakage. It has been modeled with capacitors that are representative of the actual parts themselves. So you see these are part numbers for our aluminium electrolytics, MLCCs, polymers, etc. So we are seeing the actual behavior of the various different parts. And we map these to the actual design parts on the schematic. So they're not just what's available in terms of a transistor. No, we try to make sure that we are using the BSZ 16, blah, blah, blah. Okay. Output was beautiful, 12 volts on the dot pretty much. Switching frequency we set for this design at 200 kilohertz. And we ended up with nice continuous conduction mode as we would expect for the design. So nothing untowards. This is here showing you the simulation of the filter that I have put together. And what I have done here is, like you saw on the earlier slide, just I've sectioned the filter into the various different stages, as I promised you at the very beginning. So we've got differential mode for radiated emissions. We've got differential mode for conducted emissions, common mode for radiated and for conducted, differential mode for conducted. So all of these were considered as part of our complete filter design for this stage. The reason for doing this twice is because I wanted to run the simulation to see differential mode output and common mode output. And that's what you see on the next slide. Insertion loss. So we get about 80 dBs or so at a 200 kilohertz differentially, and around 35 dBs or so common mode out of this filter, which is really fantastic for what we're getting. So now I'm inviting you into our Ohm Suite Ohm, which is our lab facility that we have in our Manchester office headquarters in the UK. And you can see the setup that I have put together to test this board. There's the design that you saw in the earlier picture with all of our components here, the cap, the common mode chokes, and the little coupled inductor. And there's me probing in onto the drain source signal of the MOSFET, or the switching node of the FET. So on here, you will see on the following slide is the signal. That signal that you see here is the one associated with that drain source signal. Okay. So we started off by looking at the conducted emissions trace for this design. We used a CISPA25 LISN that we designed ourselves. It's a dual LISN. And we really had to test this using the FFT function on the RTA 4004 oscilloscope that we have in our lab. But we also had to repeat the measurements using a spectrum analyzer because this was really, really low noise. I mean, if it wasn't for this here, I would have thought this is some joke or something that's not switched on. But no, this is real. We didn't get much in the way of noise. The filter is doing its job fantastically well. So great. So switch off more, its work is done, your job is 100%. No, not always like this. So what we ended up going into is, as I always do in designs, is look around the board, check signal integrity, do load and line transient, look at voltage regulation across the input, output, etc. And make sure that everything looks as it's supposed to look from a signal point of view. And this is when I discovered this. So this is the same operating condition that we'd simulated earlier, where we saw a nice continuous conduction mode, drain source signal was nice and square. Now we are seeing some kind of mistriggering, some kind of an instability. So this was something that is worthy of further investigation. So I did a lot of root cause analysis investigation into this to find out that unfortunately it was not something as basic or as simple as a control issue or an instability in the loop. It was more associated with layout and tracking. This brings us to the key of this side of the presentation is we can make a design work perfectly, or we can have issues with the design if we don't lay out and track appropriately. Now, there were a few things when I asked the customer to send me the layout and the tracking that they used to do that board that I identified, grounding connections, no separate grounds, but these weren't the critical ones. The critical ones were the feedback signal coming back from the output was shadowing a switching signal of the auxiliary winding. So that was pumping or coupling a lot of noise onto that signal. And the current sense signal that you saw earlier was also overlapping the FET switching signal. So before hacking the board and starting to cut tracks and reroute things around, I thought, well, better check my theory. Otherwise, unless if I'm wrong, then I'm in trouble. So what I've gone and done is try to model the behavior of that coupling capacitance that I'm getting because of the overlap between those tracks. Now you can do this using various calculators online that will calculate capacitance between two tracks based on FR4 or pre-preg material. In this case, it was just a standard FR4, it's a two-layer board. And I took the dimensions of the tracks, the thickness, the ounceage of copper, etc., and dumped it into this calculator. And I got these types of capacitances as coupling capacitances that were impacting those signals. So I simulated this in LT-SPICE just to see what behavior I'm going to get. And lo and behold, I was very pleased, to be honest with you, to see that in LT-SPICE, I was pretty much getting the same shape signal that I was getting in practice. So it gives me a warmer feeling, at least now, that if I go and hack the board, that yes, it is more likely to be associated with layout and tracking. Voltage simulated was also quite stable. Like we were seeing earlier with the testing, voltage was 12.07 volts, so as well. Okay, so to finish off, just to give a quick summary and conclusions about what we've talked about so far with regards to this layout and tracking. The design was fine. Regulation was very good across load and line conditions. Efficiency, as I said, 87%. Thermal performance was very, very good. Up 42.4 degrees was the hottest spot on the board. conducted emissions, sorry, I don't know about radiated. Conducted emissions performance was very good, but it has been designed as well for excellent performance from a radiated point of view, but that's what I tested, at least, conducted. However, layout and tracking resulted in the signal integrity issue that we saw. So in general, with layout and tracking, what I found is it can be quite difficult to identify the problem if it is a layout and tracking related issue. And it sometimes may not result in an immediate failure, as we saw here. There was no failure, but the problem is this could manifest itself in a latent failure. So it is important, in my view, to once you identify this, to modify the board and correct it, get it right, because you never know when it might come back and bite you on the nose in future. And in some other occasions, layout and tracking can just result in an outright failure. This might not work from the beginning. So in conclusion, a good layout and tracking is essential. For what? For with good filtering, yes, to get good EMC, electromagnetic compatibility, but also to ensure good functional performance. We don't want failures further down the line, in other words. Okay, I'm conscious of the time, so the last section I'm just going to run through very quickly. And the main key really idea behind the general interfaces section is just to tell you on our website, we have now created a link called Applications Guide, which is available in these slides, which will take you into various different types of set interfaces, Ethernet, USB, CAN, etc., and provide you with filtering, EMI filtering, and including overvoltage protection, I should say, for all of those interfaces. It's doing the job for you. Take advantage of it is the advice. So there's a USB example here, USB 2, USB 3. And there's an integrated solution for a USB-A type solution with actual filtering included in the back shell if you don't want to change the PCB. That's another design. We also have a filter board for USB-C, actually the very popular now interface. So this is fully protected both from a super speed, high speed, and a power interface filtering point of view. There's an application note associated with that USB-C, as well as one associated with this RS485, as well as the design that you can see here. The same, I think, applies for Ethernet, where we also have the option for you to select a transformer that's high performance, low emissions, with 2 stages of filtering, one on the cable side and one on the PHY side, for additional insertion loss. To help out as well, Würth has always been very forthcoming in providing evaluation boards to build your own filters on ahead of you going to EMC testing. That saves you a lot of time and grief if you're going to have to go and spend so much money doing testing in-house, testing in a test house. Might as well take these filters with you and try them out while you're doing the testing as to have to build them over there. So that's also a very useful facility that we have. We have got the PCBs, and naturally the equivalent components that you can use for these. I mentioned before mains filtering. I also I'd like to maybe mention that we also have these set modules, filter modules for the mains. The nice thing about these modules is you don't have to think about it, just plug and play. And we also have simulation models for these in LT-SPICE, which will help you know and try to look at the behavior of this if you wanted to simulate it as part of your overall system. I finish off my slide with, for those of you at least in the UK, inviting you to our next big event with Rohde & Schwarz. It's more power related than EMC related. It's going to be held on the 10th of October this year, and it's going to be a workshop more than a seminar. It's going to be very practical. Various different aspects of practical designs of power supplies, and it's held in Birmingham, UK, as I said, and we are giving away to a lucky winner an RTA Rohde & Schwarz oscilloscope as well. Thank you very much for listening to me and for your attention. I hope you found this useful, and I think it's time for questions.
Yeah, thank you, Mo, for your interesting presentation. Like you already said, let's have a look to the questions. There are already some which came in during your presentation. Maybe we can start with the first one.
Sure.
Question about surge testing with a multi-stage input filter. We had problems with ringing at the output of the filter. Is there a recommendation for damping?
Yes, multi-stage filters and generally having filters on the front end sometimes can exasperate, let's say, surge testing and end up giving you higher peaks and higher voltages than you would tend to have as a result of the surge itself. So it is something that I have come across before. I used to work in the aerospace industry, and we used to do pin injection testing on pins on various different interfaces on the units, on our units. And in some occasions, yes, of course, the filtering that you can put in will result in this. But you can damp this. It will help with the damping side of things. But I would suggest maybe also trying to use some level of transient voltage suppression if you don't already have something there, to try to clamp that voltage to a more reasonable level, let's say. So whatever maybe ringing or resonance that you might see is automatically, let's say, clamped as opposed to damped by a proper designed transient voltage suppressor. I hope that helps. I hope that answers the question.
We will see. Otherwise, he can just wrote us a mail.
Absolutely.
So, next question. You always introduced an extra capacitor with resistor when damping is needed. Is that better than just introducing a resistor for the existing capacitor?
I'm sorry, I did not hear that very well, Lisa. Where's the question?
Okay. It was the question from which was at 10:26. Can you see? You always introduce an extra capacitor with resistor when damping is needed. Is that better than just introducing a resistor for the existing capacitor?
Oh, okay. Oh, yes, I can see the question. Thank you, and yeah, thank you for your question. The idea behind having a second capacitor as opposed to just putting a resistor with your standard filter capacitor is just to try to keep the performance of your LC quite good. So you need that roll-off to still be quite sharp. And the introduction of the extra R and C, what that does is it tries to maintain the sharpness of the roll-off at 40 dBs per decade as you go up the frequency range, but damp that big ringing or resonance, I should say ringing, that resonance at or overshoot at the cutoff. So again, I mentioned before, we try to have the cake and eat it. That's the methodology. There is also other ways that you can damp. You can damp with a series resistor with the inductor itself, for example, or use a higher resistance inductor, but that's not efficient. That's not necessarily an efficient way of doing it. So for me, the use of a very small resistor in series, which is not going to be dissipating power, so you don't need a fancy resistor there. It's a reasonable solution to do it like that. But that's the reason why we don't just put it with the filter capacitor directly.
Okay, thank you. So I think we have to go to the last question. Cost of the time to the other questions, we will answer them afterwards via email. So last question, where can we get Würth LT Spice models?
Okay, that's a very good question. So with LT Spice models, they are available to download from our website. They are now available associated with every component. So if you go onto the website and select a particular inductor, chip, bead ferrite, capacitor, you will see that next to that there is a drop-down menu. That drop-down menu includes all of the models, be it the cadence, the step files, layout and tracking files, but also it will have the P-Spice as well as the LT Spice models as well. That's one way. The other way is within LT Spice itself. Now we have got what's called the contributors folder in LT Spice. If you just do a sync release and update the tool to the latest revision, what you will get is this contributors file. Würth were the first contributors file or contributor to that folder. You will see not all, but quite a lot of our components now available in that contributors folder. And they keep being added on a regular basis. If you see something that's not available, please find it on the website. If not, do contact your local salesperson or FAE, and we are more than happy to support you with finding the model for you. if it's not available.
Okay, so thank you very much. Now we are finished with the presentation, and thank you for your attention. I hope you enjoyed our presentation. The next presentation topic is essentials for the design of a GB Ethernet front end, and starts at 11. So see you there and enjoy our digital days. Goodbye.
Thank you. Goodbye.